day. Oh, good morning. My name is Mark Lipton from the University of Guelph College of Arts. Thank you for having us today, and I'm honored to be facilitating today's talk. Usually, when I begin some kind of talk like this, it is my custom to share with you a gift, something sweet, like chocolate. Anyone like chocolate? Something to stimulate your senses, wake you up. These are strange times. How do we come to be both here and not here, talking with you through human-made tools about environmental stewardship? We are well aware of the circular ironies that deck and double back in these remediated worlds. Simultaneously present, yet alarmingly nowhere to be seen. In this vein, we want to ask you about the air you're breathing right now. What does today's air feel like? Air is life-giving. How does the smell of today's air evoke for you a vivid mental image of some other time or some other place? And in this spirit, to be here and not here, simultaneously present, yet alarmingly nowhere to be seen, I ask you to accept a mini proverb from my culture. I see my culture as meaningfully remixed, part Jewish, Yiddish, a few Buddhist tendencies. I call myself a Jubu and speak to and through my ancestral grandmothers, past, future. Their oral histories and epistemic knowledge is my body, revealing a magical kinship with all things sentient and earthbound. I can hear Bubby Gietel's voice echoing now. Ik ken nicht tanzen mit alle Chassen, mit ein Tuchas. I'll say that again. Ik ken nicht tanzen with alle Chassen, with ein Tuchas. You can't dance at two weddings with one derriere. Bubby Gietel, I am both here and not here, simultaneously present, yet alarmingly nowhere to be seen, just like you. It is in this spirit that today we come to you in peace. We recognize that each First Nation possesses both individual and shared heritage, culture, languages, and systems of governance. As this land's original keepers, we recognize Indigenous historical relationships with the land, and this stewardship continues. We work and live and try to make kinship with a deep respect for this earth, all things, and Indigenous stewardship and leadership.
The state of Arctic air has arrived at a fork in the road. Both paths lead to massive ecological change. How do you know which path to choose? Which path is a trap? Which path leads to possible solutions?
Let's look to Environment and Climate Change Canada scientists for some answers.
Hi, my name is Hayley, and I'm a research scientist of the Air Quality Processes Research Section of Environment and Climate Change Canada. I study human-made chemicals in air in sensitive ecological systems such as the Arctic and the Great Lakes.
When Hayley travels up north, she loves meeting people from different communities and listening to stories about their land and culture.
Hi, my name is Liisa Jantunen, and I'm a chemist from Environment and Climate Change Canada. I've been researching contaminants in air and water in the Arctic for the last 28 years. Recently, my research focus has been looking towards microplastics.
Hey, Liisa, does this new research focus mean that you're on those gigantic Coast Guard ships collecting samples?
Yeah.
Hi, my name is Alexandra Steffen, but everyone calls me Sandy, so please call me Sandy. I am the lead Mercury researcher for the Atmospheric Processes Research Section at Environment and Climate Change Canada. I specialize in trying to explain how mercury behaves in the air. I run several mercury sampling programs to understand the levels of mercury in the air on local, regional, and global scales.
Sandy, Don't stop there. Let's celebrate your recent work at the interface of science and policy.
I was appointed to the Canadian delegation for the Minamata Convention on Mercury, where I get to help Canada negotiate our position on the international level when it comes to issues of mercury in the environment.
Thanks, Sandy. Sandy is most known for her long-term work in the high Arctic, and in the springtime, Sandy can be found traipsing across sea ice collecting samples. Thank you, Sandy, Liisa, and Hayley.
Thank you.
Thank you.
Thank you. The work that we conduct could only happen because of support from national programs under Environment and Climate Change Canada, the Northern Contaminants Program, the Chemicals Management Plan, and ArcticNet, as well as international programs such as the Arctic Monitoring and Assessment Program.
We also want to highlight and give a big shout out to our Indigenous communities and partners from many regions of the North who have helped us develop and work on our programs. This research is a community effort and continues with your determined support. Thank you.
Thank you.
Today's presentation is organized into 4 parts. First, we share the intensity of science and tell you what we do. Second, we identify and describe why it's important to study contaminants in the Arctic. Third, we answer the question, what is Arctic air pollution? And 4, we conclude with ideas about the bigger picture. In our role as scientists, we want you to know how science can drive social and ecological change.
Sandy, Liisa, and I have all worked together in air research for a long time and have almost 75 years experience between us. Many of you already know what air pollution is. We study contaminants, a subsection of pollution that refers to potentially harmful, toxic substances not normally found in an environment. We study how contaminants that are emitted by human activities get into the air and how they affect the Arctic environment. Our work is primarily under a program called the Northern Contaminants Program, which conducts long-term monitoring and surveillance of chemical pollutants in air as well as in wildlife. We have been measuring persistent organic pollutants, mercury, and more recently, microplastics at many places in the Canadian Arctic. For a long time, we have been collecting information from ALERT, which is located on Ellesmere Island. ALERT is the world's most northerly station where these unwanted chemicals are being measured. In fact, they have been measured continuously since the 1990s, so it's actually the world's longest measurement program of these pollutants. We also have another station in the Yukon, close to Whitehorse, called Little Fox Lake. And Little Fox Lake is marked on this map in purple. In 2014, Sandy and I partnered with 7 communities. The red dots on the map are where our partners are. In these communities, we collect air samples for both persistent organic pollutants and mercury. Collected samples are sent to our labs in Toronto to be analyzed, where we determine the amounts of persistent organic pollutants and mercury in the air.
Part 2. Why we care about contaminants in the Arctic.
We now share 7 important reasons why we study contaminants in the Arctic. 1. Our planet and all living things exist in a delicate ecological balance. Ecology refers to the branch of science concerned with the interrelationship of organisms and their environments.
As an environmental scientist, we are tasked to look at aspects of the ecological system for patterns and relationships between the living and non-living parts of the environment. From this information, we try to assess when the balance in the ecological system is off. 2. Part of the work we do is to track changes in the Arctic pollution levels, assess the risks to the ecosystem, consider impacts, and help reduce the future risks. 3. Contaminants from around the world travel to the Arctic and gather in the Arctic. These contaminants stay in the Arctic like a bad house guest.
Birgitte would say, a gast is wie ein.
4. Contaminants are toxic and may impact Arctic environments and communities. They are something people don't think about that are impacted by climate change. 5. Contaminants do not degrade easily. In fact, these chemicals may multiply through processes called bioaccumulation and biomagnification. 6. Contaminants can impact wildlife and can pose risk within the ecosystem and to humans.
And our last concern, 7, is really our major concern, and it lies in the impact and exposure of contaminants on northern people.
Now we're going to tell you more specifically why we are concerned about Arctic contaminants as environmental scientists. Contaminants such as persistent organic pollutants and mercury are toxic chemicals that should not be found in high levels in the Arctic. Microplastics are often found in the Arctic where they should not be found at all. As contaminants travel to the Arctic, they make their way into the ecosystem, into the wildlife, and eventually into humans. The primary route of exposure is through the consumption of country food that contains these contaminants, which can be unhealthy for humans. Our role is to try and understand how contaminants get to the Arctic and figure out what happens when they get there.
Why do we care about persistent organic pollutants, or POPs in short? Actually, we call ourselves pop stars. I have 4 answers. First, these chemicals can stay in the environment for a long time. Once emitted into the environment, they don't break down easily. It might take hundreds of years. Second, it doesn't matter where POPs or persistent organic pollutants originate from. Wind and water carry these chemicals far from home, eventually taking these chemicals to the remote Arctic regions. Third, persistent organic pollutants are toxic. For both wildlife and humans, exposure to persistent organic pollutants may result in health problems. My last point, 4, these unwanted chemicals have a tendency to accumulate through the food web. They are known to accumulate at the top of the food chain. When scientists study animals like whales and polar bears, higher levels of persistent organic pollutants are found in their systems. This is the result of 2 processes called biomagnification and bioaccumulation. First, let's talk about biomagnification. For example, when pollutants get into the water, they get absorbed by tiny shrimp and algae. When small fish eat these tiny creatures, the chemicals are magnified. And as large fish eat the small fish, more and more of these chemicals magnify. The larger the fish and animal, the more the chemicals have magnified. As whales eat more fish, these persistent organic pollutants biomagnify. Then let's consider the second process, bioaccumulation. Bioaccumulation refers to the process where the amount of chemicals accumulates in the animal. When animals consume food containing unwanted chemicals, these chemicals accumulate over the animal's lifetime. As Arctic fish and animals get older, just as we age over time, the amount of unwanted chemicals increases.
Why do we care about plastics? Plastics are everywhere. We are constantly exposed to small little bits of plastics. Plastics can have physical effects on animals, especially when animals mistake plastics for food. The plastics make them feel like they've eaten enough. Their bellies are full, but plastics have no nutritional value. Animals sometimes get tangled or stuck in plastics. Imagine what happens when these animals consume plastics, how it impacts their insides. As Hayley explained earlier, plastics are passed up the food chain when small creatures eat plastics, and then they're eaten by fish, and then they're eaten by seals. Like other contaminants, as plastics pass up the food chain, they can bioaccumulate and biomagnify.
We just talked about what we do. Then we outlined 7 specific points and went into greater detail about why we care about contaminants in the Arctic.
In short, we care because northern people and wildlife may be exposed to and experience negative effects from contaminants.
Now, we turn to the contaminants and take a look at what we study in more detail. Many human activities emit chemicals that contaminate the environment. Things like mercury travel from around the world into the Arctic. That's Sandy's expertise. My area includes pesticides, industrial emissions, and commercial chemicals. Every day, humans use chemicals that can also contaminate our environment. Commercial chemicals include, for example, pots and pans treated with non-stick coating. Did you know that hamburger wrappers are coated with liquid repellents to prevent the juices from soaking through the wrappers? This coating is another commercial chemical. And finally, microplastics are now found everywhere in the environment. In a minute, Liisa will talk about plastics. First, let me tell you about a particular class of chemicals that I study called the persistent organic pollutants. Persistent organic pollutants make their way to the Arctic through a process called the grasshopper effect. When these chemicals are emitted in tropical regions, heat and high temperatures make the chemicals rise into the atmosphere. They will then piggyback onto the wind and travel north. Right now, I'm in Toronto, cold in the winter and hot in the summer. In the winter, persistent organic pollutants fall to the ground and onto the land and ocean surfaces. But when it's hot, they evaporate into the air where wind and air currents take them to the Arctic. Persistent organic pollutants that we study do not occur naturally. They are mostly human-made. There are three main classes of persistent organic pollutants. First, industrial chemicals include things like PCBs, flame retardants, and stain repellents. You can find PCBs in old transformers. Flame retardants are chemicals found in your sofa, preventing fires. And stain repellents are like those chemicals I described earlier when I was talking about hamburger wrappers. Some food packaging materials are coated with liquid repellents made with these chemicals. Second, pesticides that kill bugs. For example, DDTs kill mosquitoes to help control the spread of diseases like malaria. The third class is exhaust, like smoke when you burn wood. Exhaust refers to combustion byproducts. So, for example, a car engine produces exhaust. What comes out of your car's tailpipe?
Mercury is a little bit different than persistent organic pollutants in that mercury is natural in the environment. We may know from our periodic table of the elements that the symbol for mercury is Hg, capital H, small g, which stands for hydrogium, or quicksilver. In nature, it's mostly found as a rock with some beautiful redness to it, and that rock is called cinnabar. In some spots, mercury can be found in the ground as silver liquid. When you see a thermometer, it's the silver mercury that rises and falls with the temperature, telling you how cold it is outside. Dentists sometimes use mercury in people's teeth as fillings. This isn't common practice in Canada, but it's still done in some places. I have many mercury fillings in my teeth. Someone mentioned chocolate. Mercury can also be distributed to the atmosphere naturally through things like forest fires, volcanic eruptions, and it even comes in and out of the oceans and water systems. Those are the natural forms of mercury. However, mercury is released into the air through anthropogenic, that is, by human activities. In fact, the amount of mercury in the environment has been amplified by at least 3 to 4 times because of mining activities, metal smelting, the use of mercury in consumer products, coal burning, and artisanal scale gold mining. So that's the dichotomy of mercury. It's natural in the environment, but humans and human industries are unaware of the consequences when mercury is added to our environment. There certainly is a lot more mercury than what should be there.
Microplastics. What are they? We all know what plastics are, and plastics are great. We use them for so much. I can't imagine life without them. The problem is, generally, we use them once, and then we throw them away. We try to recycle them, but most end up in the landfill, and some end up in our wider environment. We find microplastics everywhere. We find them in the deepest Arctic sediments. We find them in the high elevation mountains. We are living in a world polluted with microplastics. Tiny sized microplastics are fibers, fragments, beads, smaller than 5 millimeters long, about half the width of your thumb and smaller. A penny displayed with tiny microplastics help give us a sense of their relative size. Plastics do break into smaller pieces, especially when in the ocean. Plastics never disappear. They become smaller and smaller and smaller, but plastics do not break down chemically, returning to the original carbon and hydrogen. Where do microplastics come from? The manufacturing of plastics. Raw plastic materials, often called nurdles, are simple beads of pure plastic. These are sometimes found on beaches and are referred to as mermaid tears. Other sources of microplastics are a result of the breakdown of larger plastic debris. For example, the breakdown of polyethylene plastic bags, like what your grocery store uses, if your grocery store still uses plastic bags. Plastic fibers released from textiles, either during manufacturing or laundering, are a major source of plastic pollution. Of course, plastics are never just plastics. I mentioned the manufactured nurdles, but most plastics contain all kinds of other chemicals. Hayley mentioned some of these. Plastics contain flame retardants to help prevent fires. They contain phthalates, which makes the plastic more flexible. They also contain chemical dyes for color and UV filters so plastics won't fade in the sun. This makes microplastics a chemical soup. Microplastics can also attract other chemicals from the environment. They can pull in chemicals like mercury and other toxic metals. How are humans exposed to microplastics? We mostly think of microplastics being in our food, like bottled water. No. A recent scientific study discovered that humans are mostly exposed to microplastics through the inhalation of fibers. It's in the air. A lot of microplastics also go down the drain when you wash your clothing. These days, a lot of clothing is made from plastic synthetic fibers or synthetic materials combined with cotton. But both materials release a lot of microplastic fibers. We breathe in these fibers. In fact, a major way microplastics can impact human health is through the air. Microplastics cause inflammation. There is increasingly more work being done, but more research is urgently needed.
Part 4. How science drives change. There's a bigger picture to the science work we do. We are driven to do our research because what we discover helps drive local and global change. We now spend our last few minutes sharing how we participate in social and ecological change. Because we're government scientists, we produce high-quality scientific information. Our work also provides information to governments who use our research to guide pollution control and other environmental policies. The scientific method begins with careful observations. In our case, by paying attention to ways that the Arctic air might be contaminated. We design our experiments about the environment that produce verifiable results. This means that if I wanted to test another scientist's research, I should be able to follow their procedures and arrive at the same factual results. Understanding the facts of science is important, and because we are government officials, our facts must make sense to the general public. When Canadians have questions or concerns about the environment, they direct those concerns to their elected officials, who call on policymakers to make government rules that we all must follow to protect our environment. The facts that come to light because of our scientific research are used to inform global policy on the current state of science. The scientists and policy folks work together to produce reports. This information is then crafted into national policies or rules that attempt to reduce the pollution in the Canadian environment. As federal government scientists, we are firmly committed to and engaged in this process, and our job is to provide non-partisan scientific advice to the government of the day.
Over the years, our scientific research has provided facts for policymakers in Canada and internationally. Our facts are used to craft rules that protect the environment. Because pollutants are used all over the world. Because pollutants are emitted from all kinds of sources. And because pollutant can be carried by wind and water, moving to remote places like the Arctic. It is important that everyone in the world follow these rules that help reduce these chemicals from traveling to the Arctic and harming its environment. Global agreements under the United Nations control and restrict these pollutants, including the Stockholm Convention, which controls the production of persistent organic pollutants, and the Minamata Convention that controls mercury. Liisa's work now provides scientific information for making regulations about microplastics and plastic waste. Her work will feed into Canada's plastic science agenda and the Ocean Plastics Charter. We provide our non-partisan science advice to our Canadian government representatives who negotiate with government officials from all over the world. Then, global regulations like international laws and agreements are enacted to reduce or remove these pollutants.
It takes every human on this planet to follow these rules.
We want to prevent harmful pollutants from entering the Arctic, and we use science to protect and preserve Arctic environments and people.
In closing, we shared 4 big ideas about our work and our concern about contaminants in Arctic air. 1, we told you about our work as scientists, what we do. 2, we outlined our concerns about Arctic air pollution and shared 7 reasons for studying Arctic contaminants. 3, we answered the question, what is Arctic air pollution? And described the specific contaminants each of us studied. And 4, we looked at science from a larger frame and shared some important ideas about how science can drive social and ecological change.
Each of these elements of our work gives a significant opportunity for hope. Change is possible.
It's absolutely possible.
Through local engagement, ongoing and additional research, and through policy interventions, science helps drive change.
Science helps drive change. Thank you.
Thank you.